In this lesson, we're going to be looking at the volume of some solids, and we're going to take this first page to develop some ideas about that. So anyway, here we have a set of axes, and on the set of axes we're going to have a function f of x, looks like this, and I want to talk about this function bounded between x equals a and x equals b and the x-axis, which creates this region here, R. Now, in the first lesson, we talked about the area of that region, infinitely summing rectangles, and let's draw one of these rectangles. I'll draw it here in pink. Alright, now we're going to look at a solid after revolution. So suppose I took this area R and I revolved it around the x-axis. So picture that to be some plate or plane of the region R and spin that around the x-axis. The result of spinning that around the x-axis would make a solid region, and it might resemble the shape of, let's say, a vase, but the vase would be filled with cement because it's a solid or dense object. So to develop this, think of taking this rectangle and rotating the rectangle about the x-axis. So that shape would be something like this after revolving it. And this is a skinny little disc. We call this a disc, or you can think of it like a poker chip, real skinny poker chip. And what is the volume of such circular disc? So this goes at the top. The volume of this circular disc would be pi r squared, so pi times the radius squared, and then times the height. But when you think of a poker chip, you wouldn't say, oh, that poker chip is really high. You would say that poker chip is really thick. So I'll say pi times radius squared times the thickness. That is the volume of a disk. And this illustration here shows that we can approximate the volume of the solid by summing up these disks. And so we would say here that the volume is approximately the sum of each disk. Each disk has a volume of pi. The radius, as you can see here, the radius goes from the axis out to the edge of the disk. Here you might see it from the axis out to the edge of the disk. So the radius is going to be f of x. And then the thickness of each one of these is going to be delta x. Again, the volume is approximately the sum of all of those disks. And then to get the real volume, the actual volume, well then that's going to be the infinite sum of a whole bunch of disks. So we're going to do the integral to represent the infinite sum from a to b. That says the first disk occurs at a, and the last disk occurs at b, and we're going to add all the ones in between it infinitely, infinite sum. So the integral from a to b of pi, again, the radius is f of x, and that gets squared. And then the thickness now becomes this incrementally small value dx. Now, in a similar illustration, this time we have this green curve. Now, you might notice that this green curve is not a function of x, but it could be a function of y. So we could say x equals g of y. And if I had this region R and I wanted to rotate it, I would consider looking at a rectangle and then rotating that rectangle. If I rotated the rectangle, again we get this circular disc that looks like this, has the same formula, pi radius squared times its respective thickness. This next diagram shows the sum of a bunch of these disks, and we can review and say the volume is approximately the sum of all of these disks, which each one is pi. The radius now would be the function g of y squared, and the thickness would be delta y. And finally, the volume of this particular solid, the volume equals the infinite sum from a to b, pi times the radius, g of y, squared times the thickness. In this case, the thickness of each one of these is dy. And so we have these solids, again, that look like perhaps a vase, but the vase is filled with concrete. These are solid or dense objects. Let's take a look at example 1. In example 1, we have the area bounded by the parabola y equals x squared plus 1. And we have a couple other curves. We have x equals -1, x equals 1, and we have the x-axis. And our area is bounded between all of those curves. Now we're going to take that region R and we're going to rotate it about the x-axis. First thing I'll do is I'll draw a rectangle in the region. Okay, we know we're going to rotate that rectangle and a bunch of others to create this shape. Let's see if we can't figure out what the shape looks like. In order to draw this, I'm going to come down here and do a mirror image over the x-axis like that, and then I'm going to make these discs at the end, one over here and one over here. If I dot 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 the inside, you get the sense of what the shape would look like. I have had people say this looks like an hourglass, and I have to laugh a little bit because it would be a pretty funny hourglass. You would turn it on its side and all the sand would fall to one side immediately. But I get the idea. It kind of looks like an hourglass. But of course we have to remember this is an hourglass filled with cement. So it's dense or solid. If I come down here and I draw the outside like that, I can then draw the disc inside, again getting the sense of what each one of these discs look like. We're ready to set up the volume. The volume equals, I'll pull out the pi, from the first disc at -1 to the last disc at 1. And then the radius, which is the key feature of this, the radius is going to be the distance from the axis of revolution out to the original curve itself. That is this distance here as the radius. And you can see that that radius is the distance x squared plus 1. We have to square the radius and then times the thickness dx. In example 2, we're going to take y equals x cubed, y equals 1, y equals 8 in the y-axis, and take the region bounded between those four curves. And we're going to rotate that region, shaded in gray here, we're going to take that region and rotate it about the y-axis. Because I'm rotating about the y-axis and I'm using a disc, I have to draw my rectangle in a horizontal fashion. Okay, let's see what this might look like. I'm going to come over here and then I'm going to draw this top disc out here and this bottom disc down here, and you might say that looks like a bowl, but a bowl filled with cement. And each disc will look like this in a horizontal orientation. This is the radius, but I hope you see here now that the radius is the distance from the y-axis out to the curve going this way. That distance is not x squared. X squared is this distance. So what we need to do is we need to take this and we need to solve for x. So this is going to be x equals the cubed root of y, or simply y to the 1/3 power. Now we're ready to set up to find the volume of this bowl filled with cement. Volume equals, from the first disk, which occurs at y equals 1, to the last disk, which occurs at y equals 8. Now it looks like I didn't pull out the pi, but that's okay. I can write the pi inside if I'd like. Now I'm ready to write the radius. And my radius is going to be the function x equals g of y. It's a function of y. And that's going to be y to the 1/3 power. I need to square the radius, and the thickness of each disk is dy. And you are free to leave it in this format. I kind of like it because I can see the radius and I see the form that the radius is squared. But you could also simplify that term to say y to the 2/3 power. That would be helpful in the event that you are asked to actually evaluate the volume.